Hello everyone. So in this video, we are going to discuss effect of armature reaction in DC machine. Basically, in the previous video, we have seen the nature of the armature reaction in DC machine is in cross magnetizing in nature, and from the phasor diagram, it seems like the resultant flux has increased, and the resultant flux, that is phi r, is more than phi f from this particular phasor diagram. But it is actually not true, and it is not true because of the saturation of the magnetic material. So you can see the direction of the resultant flux is in this direction, like somewhat here in between D and Q axis. So in the actual machine, if you try to see the direction of the resultant flux, you can draw the resultant flux waveform. Come to this figure here. You can see the direction of the resultant flux. It will be in between D and Q axis. Here again, it is a Q axis, and 0 dx, right? It will be in between D and Q axis. So this is my direction of the resultant flux, this this, and at the pole tips, for in case of north pole, at this pole tip the flux number of flux lines are more, and in south pole, in the south pole, here the number of flux lines are more compared to this pole tip. The number of flux line is more in this pole tip, and compared to this pole tip, the number of flux lines are more in this pole tip. Okay, so it is, there is non-uniformity, and these poles are basically created by like DC excitations. Okay, and it also has some saturation. It cannot tolerate this many number of high field flux. Like these are the densely populated, you can say. These are the density is too much, and it cannot tolerate. So it will go to the saturation region. So the reduction, that is the amount of reduction you getting here, that reduction you cannot compensate here by having more number of flux lines because of saturation. So even though the phasor summation says the magnitude of the resultant flux will increase, but due to saturation, it will not be true. So there will be reduction in the main field flux, the resultant field flux. Okay, the resultant flux will decrease, and it has seen, like it has been observed, like the reduction will be around 1 to 5% at from no load to full load. Okay, this reduction, and if there is a reduction in the field flux, then definitely what will happen, as you know, the induced EMF in case of generator is proportional to the flux per pole. So the induced EMF in case of generator will reduce. And if we think about motor, in case of motor, the torque is proportional to flux and the armature current. If the flux decrease, the electromagnetic torque generation in case of motor will also decrease. So these are the things that are not desired. Okay, we have to work on this issue. And if you see, in case of DC machine, you have, this is your rotor. Okay, this is your maybe, roughly if I draw, this is your stator pole, this is your stator pole, this is your Q axis, and this is your D axis. Okay, and basically this Q axis is something we call it as a magnetical neutral axis, or sorry, geometrical neutral axis, GNA. Because if it is north pole and it is south pole, in from north pole to south pole there will be a point where the magnetic flux density is 0, and that will be along Q axis only. So it is a geometrical neutral axis. At no load, the geometrical neutral axis and magnetical neutral axis will be same. So at no load, the geometrical neutral axis, and you can say it is a magnetical neutral axis at no load only. So no load means there is no current in the armature. At this condition, this GNA and MNA both are same. But in case of when you add some load in case of DC machine, then the armature current will flow, and the resultant, that there will be a tilt in the resultant flux direction, and in the direction of the resultant flux will lie in between D and Q axis. So your magnetical neutral axis will shift in the direction of the rotation if it is a generator, and there will be shift of MNA in opposite direction. If let's say if your motor is rotating in anti-clockwise direction, then the MNA will shift in clockwise direction. So there will be opposite rotation, opposite movement of the MNA in case of generator and motor. So maybe we can discuss these things later, but there will be a shift of MNA. So since this is my direction of the fire, so direction of the MNA will be here. This is my direction of the MNA, and this is my direction of the GNA. Maybe I can clean out up this section. So this is my field flux. This is my armature flux, and 90-degree with respect to field. This is my GNA. This is my GNA, and because of armature reaction, I got a resultant flux which is in this direction. So the axis which is located 90-degree of this resultant, that will be here. That is something we called MNA, magnetical neutral axis, and this is the geometric neutral axis. So there will be a shift, and it is a because of this shift you will get some other phenomena, something called delayed commutation. We will discuss these things like what is the delayed commutation because of MNA shift, what is the effect in commutation process, and all of these things will be discussed. So if I try to summarize here, so these are the main points basically. You have seen, like, because of armature reaction there is there is a reduction in the main field flux per pole, and also it distorts the main field flux waveform. Why it distorts? Because if you see inside the machine, towards one pole tip the number of flux lines are more, and towards another pole tip number of flux lines are less. Okay, it is too less. So there will be a distorted waveform inside the machine, and there will be shift of MNA in case of DC machine due to armature reaction, and there will be delayed commutation. So all of this phenomena we'll be discussing in upcoming videos. So if you have any doubt, you can write down your query in the comment section. Thank you.